So, what are phase portraits? How do we interpret them? Assuming that we have the prerequisites and that you have been basically checking the stuff here and feeling that you know the stuff here, and that you have been doing the self-assessments, okay? This assumption is going to be a recurrent assumption, so I do not go through the self-assessment on the PLOs, on the prerequisites learning outcomes, okay? Otherwise, we do not finish the course, okay? So it's something that is for you. Are we aligned on this, people? Perfect. Okay. Let's go. And applications is something for the people that want to know. We have our lockable terra. Whenever we take a point here, we will have a point on the foxes dot, rabbits dot, and let's say that this vector here identifies this vector here. Okay, together? Let's assume this. Will my trajectory look like this, 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 or you do not know? Go, discuss. So, what would you say, people? What would you say? Everybody answers, please. 1, because this indicates that I've got positive derivative on the foxes, positive derivative on the rabbits. It means that I go right and up. True? You see it? If I were to have a trajectory looking like this, if I were to have this green trajectory here, where should my y dot be? First quadrant, second quadrant, third quadrant, fourth quadrant, 5, you do not know. Let me rewrite. So this is foxes dot, and this is rabbits dot. Yeah, sorry for this. I'm gonna fix it. So what would you say, people? Rabbits is increasing, foxes are decreasing. 4. Okay, together. Now, if I do Euler, and I do Euler and I find this point here, and then I continue iterating Euler, I will find something that looks like, and then I iterate. What is this stuff here? This one is called phase portrait. This is basically the visualization of the trajectories of a system starting from different initial points, different initial conditions, okay? And we will see them not in time, we see them in space. If I was taking, so this is a bad kind of drawing, but this is rabbits and this is foxes, okay? Tomorrow you're going to create your own, you're going to see it even better. In a certain sense, if I look at this signal here, it's not a signal, but we will see if rabbits is green and foxes is in violet, we will see foxes that do like this and rabbits that do like this. And I'm putting it in a bad way, but you got the point. It's something kind of, tomorrow you see it. Tomorrow you see it. You're going to make it by your own. Okay? So each one of those curves is basically how to look at something in time. Instead of in time, you see it on the face portrait. Okay? You see it? Let's make another example that you're going to see it. This is the face portrait of something for which here I've got theta and here I've got theta dot. Okay? And I got something that does basically goes and then goes to 0. Would you like that I show you how it looks like, the physical system? Look at me. 1, 2, and then I do like this. This is a pendulum. With friction, without friction, or you do not know? It collapses somewhere, and at a certain point, y dot goes to 0. True? If y dot goes to 0, means that I'm losing energy. True? Together? This one, what is it? Pendulum without friction. Pendulum without friction. Which trajectory is this one? Oops, I hope you get the point. Which trajectory is this one? Discuss among in the table. Perfect. Now, the people that is in the group explaining to the, like, oh, I think it's this one, this one, this one, that same persons explain this trajectory, which one it is. This one. And that's like this, and that's like this. Okay, go. The same persons that were explaining before, now the same persons explain this new trajectory. Now when we do a pause and then we finish this exercise and then
right. So this is system theory. Do you have this in the 5-year as well, or is it just the 2-year? Just 3-year. Well, in my 5-year plan, what is this correlating to? Yeah, I know, but like, what class would I have? This is like similar to, or this like kind of a combination?
linear systems.
Okay, gotcha. Filter. Gotcha.
People, how are we? How are we in terms of understanding and being able to explain this trajectory here? Which trajectory is this one? So the one that goes from here to here corresponds to the pendulum that does like one turn and stays there. True? So basically it starts with epsilon velocity and stops after an infinite amount of time back there. And this one here that I was drawing here is instead something for which you do like this, but then you go on another time and go on another time. You see? Together? The closer this one gets to this point, the more time it's going to take to do the rotation. Together? And this one is going to be something that is very fast. True. Rotating very fast. And indeed, theta goes to infinity. Okay, together and nothing. Okay, now let's do stop. Are there questions? Are there questions? Yeah.
Those ones we have theta dot and theta, and it's a fair portrait because it's a function of the second order. Okay.
Yeah, because essentially the phase portrait corresponds to what you see in the domain. It's an excellent question. Let me go back to something that we're going to see. Where is Lotka Volterra? This one. If we go back here, rabbits, foxes, rabbits dot, and foxes dot. Where is the face portrait? The face portrait is stuff that is happening here. True? You see? So basically, the face portraits represent in time what happens on the right-hand side of the equations. Together? Other question was an excellent question. No, and then we do like this. We